Okay, this is a little mini lecture to help you on your um, the lab that we had Thursday, the addition and resolution of vectors. I'm going to help you with the first vector addition 1 from the lab. So let's share the iPad, and it should come up shortly. There it is. So you were tasked. Vector addition 1 was to you were given two vectors. F1 is 0.200 kilograms times g newtons. 200 grams at 200 grams at 30 degrees and 200 grams at 120 degrees. So that's vector addition 1. We're going to do it graphically. It's shown here. This is the graphical method. So I've got F1, it's 200 units at 30 degrees. And then I've got F2, 200 units at 120 degrees. Well, what we're going to do is we're going to move the tail of F2 to the point of F1, to the arrow of F1. And so there it is. Let me make it a little smaller so that you can see it. So I've moved the F2 over to F1. Now we draw from the tail of F1 to the point. I haven't drawn the arrow yet, or I'm not going to draw the arrow because it'll interfere. We draw an arrow from the tail of F1 to the tip of the representative of F2. That is F2. You can move a vector anywhere you need to. If you did the Walter Fent experiment, you'll know exactly what I'm doing. And that is our resultant. Now, if you can measure that, if you measure that with, it's a little hard to do on the iPad, but if you get a compass, you should get about, whoop, wrong one. If you should get, let me make it a different color so that, I believe it's about 75 degrees. So that's how you do it graphically. You draw F1, you draw F2, then you reproduce F2, move the tail of F2 to the head of F1, and draw the resultant from the tail of F1 to the tip of F2, and you get your resultant. Measure the angle, the new angle from the x-axis. This is the x-axis, this is the y-axis. Measure the new angle from the x-axis, and that's your angle of the resultant. And you measure R, and you should get, I think that it's about 200, whatever you use for your units. If F1 and F2 were 200, R is going to be 283. Okay, so that's the graphical method. Now and you want to do it about this size. I mean, you want to use almost the whole paper. You don't on this example here. This is just for demonstration purposes, but inside the circle, that's really too small. You don't want it to be that small. You want it to stand out. You know what? Let me take away these lines. They might be a distraction. Okay, so there's the graphical. Now we're going to do the analytic method. So we have the 200 at 30, 200 at 120. Now we're going to resolve those into components. So if you take F1 at 0.2 G newtons at 30 degrees, you get 0.2 G newtons times cosine of 30. You get 0.173 G newtons. And F1Y is 0.200 G newtons times sine of 30, which is 1/2. So you end up with 0.100 G newtons. And in the text, it explains why we're using G newtons. So F2 is 200, 0.2 G newtons at 120 degrees. So F2x is 0.200 G newtons times cosine of 120 degrees. And you end up with a minus 1 or minus 0.100 G newtons. And you can see that on here. You can see that it's negative. It goes in this direction. And that's where the minus 0.11, minus 0.100 G newtons comes from. F2y is 0.200 G newtons times a sine of 120, and you end up with 0.173 G newtons. Okay, now to get the resultant, you add the components, like components. So F1x and F2x. So F1x is 0.173 G newtons, and F2x is minus 0.100 G newtons. So you end up with 0.073 G newtons. Ry, F1y plus F2y, is equal to 0.100 G newtons plus 0.173 G newtons, and that's equal to 0.273 G newtons. Now, to get the magnitude of R, this I really should. Oops, let me change colors. I really should represent it this way. The magnitude of R is the square root of Rx squared plus Ry squared. Well, that's the square root of 0.073 G newtons squared plus 0.273 G newtons squared, and you end up with 0.283 G newtons. So that's the magnitude. And the theta is the inverse tangent of Ry over Rx, and so that's equal to the inverse tangent of 0.273 G newtons over 0.073 G newtons, and you end up with 75 degrees. And same thing that we should have gotten from doing the graphical method. Okay, now, so that's all the handwritten stuff. I'm going to help you by showing you a spreadsheet. So let's stop this share, and let's share my, there it is, Microsoft Excel. So this is, I've set up a spreadsheet, and you can do the same. I'm not going to set up the whole spreadsheet for you, but this is how you should go about it. I've titled it Vector Addition 1, and I've got the headings: mass, angle, x, y, the magnitude, the angle, and the equilibrant. So we start off with F1. Here I'm using grams, so I'm not using the 0.2. So everything's going to be in grams. So we have 200 at 30, and we have 200 at 120. So how do I get the 173 and the 100? To get the 173, I use this formula here. You take the mass cell, the cell that the mass is in, times the cosine of the angle cell, times 180 divided by pi, and the pi has to be pi with parentheses. Why do I do that? Well, because Excel defaults to radians, and now there may be a setting where you can make it default to degrees. If there is, I don't know how to do that, so I just use this little conversion. There's 180 degrees in pi, so to convert from radians to degrees, you use a conversion of 180 divided by pi. So it's the mass cell times the cosine of the angle cell times 180 divided by pi. Now, what does that look like? Well, for this first one here, to get the 173, well, the mass cell is B3, and the angle cell is C3. Here's B3, here's C3. So the formula would look like B3 times cosine of C3 divided by 180 times pi. and you get 173. And you can do that for every, you can do that for X, F2X. You can do it for F1Y and F2Y. You can use that. You just have to put in the address of the mass cell and the address of the angle cell for your particular situation. And once you get this first one, you can copy it over here, and it should take the relative cells that you need. Okay, and then you do the same thing with Y. Now, then to add these two together, well, you can either say X. One thing you have to, if I click on here, you'll see there's a difference. I don't know that you can see this. There's an equal sign before the B3. You need to have that equal sign. I didn't put it here because it would have generated an error message. In fact, let's do it. If I put in an equals, well, how do you like that? It gave it to me. But you can't see the formula. So let me take that equal sign off so that you can see the formula. B3 cosine of C3 divided by 180 times pi. Now, to get the sum, you simply do the sum from D3 to D4. The colon says it's a range. Or you could just do equals D3 plus D4. So if we put an equals here, you'll see that it gives you indeed 73. So you need to have that equal sign in front of your formula. Okay, now we get to the magnitude. We want to get here's the X component, 73. Here's the Y component, 273. We want to get the magnitude. And so we use the square root of the X cell, which in this case is D5. The square root of the X cell squared, that's the little raised to the little caret with a 2 next to it. Oh, you know what? I've got an error here. I put X cell twice. So this should be the Y cell. Okay, so the square root of the X cell squared plus the Y cell squared. And so this is what it looks like if we put an equals in front of it. It gives you the 282. I haven't formatted these for the right number of significant figures. You should know that it shouldn't, 3 significant figures is good. When you did it on the vector table, you weren't going to get, tenths of grams, so you just round it off. And that's what I did. I rounded it off to 283. You got between 275 and 295, you were probably doing good using the vector table. Okay, so there's a formula for the getting the magnitude, the square root of the sum of the squares. And to get the arctangent, you can use the arctan, the atan function with the y divided by the x, the y cell divided by the x cell, but it won't give you the true angle. Now in this case it doesn't matter because both the x component and the y component are positive, but if you have a negative x component or a negative y component, atan 2 can give you the exact angle. So I encourage you, if you're going to use atan, to use atan 2, and you put the address of the x cell first, and then comma the address of the y cell. And of course you divide by, in this case, since it's going to return, it's in the first case where we multiplied by 180 and divided by pi, we were giving it degrees. We didn't want it to interpret it as radians. Now here, it's returning radians, but we want it in degrees. So you take the radians divided by pi times 180 and you'll get it in degrees. So if we take this and put an equals, you'll see that it gives us 75. Okay, let's, oops. There. Now, the equilibrant, so you should have gotten 283 at 75, but all that's telling you is what the resultant is. To get the equilibrant, you have to go 180 degrees in the opposite direction. And that's all I've got. I've got G5, which was 75 degrees, plus 180 gives you 255. And that was the equilibrium. That was the mass that would make the vector table balance, where that little ring was in the, would float and not bang against the pin. I hope this has been helpful. You're welcome to email me. My students, you're welcome to email me if you have any questions. Okay, let's stop the share.